Okay, so now we're on to the distal tektites. I've muddled up some medial tektites here, which from maybe Davao. Very nice core there. That's a medial tektite, and very little U-grooving, you see. It's very, very fresh. Paper thin cracks. You've got these navels here. These are Hertzian cones, formed by point pressure, basically as the shell was spooling off. They're the last remaining contact point, and because of that, all the pressure is focused on a single point, and then the shell fragment is lost, or sometimes it isn't lost. In this case, look, you can see, if I can focus, you can see that some of the shell fragments are not lost. So underneath that there'll be a navel. There'll be a Hertzian cone there, formed by point pressure. But anyway, we're looking into this cabinet for the Australites. Now, typical Australites are these core-shaped bodies. Now, note how the core is quite different to our medial tektites. You always have this equatorial scars, and you have this equatorial rim as well. You can see a distinct rim there. Now, as soon as you got that rim, see that equatorial scar and rim, you got the same on the Java tektites. They're very small, so it's hard to tell. So these ones are from Java. Very hard to get hold of. Somebody should go there and find a load more. I'm sure they exist. It just needs somebody to go and find them. Once you've got that equatorial sky, equatorial rim, you know that the tektite was previously a flanged body, but the flange is always lost, apart from on the smallest specimens, typically around 6 grams, but below 12 grams, let's say. But the typical flange button, which are specimens like this, very nice. This is a button here, genuine one. Also got some fake ones there. They're $20. These are a bit more expensive. Now these flange ones, they form through ablation. So we're in the distal regime. As soon as you've got ablation, you're in the distal regime. Tektites here were travelling in excess of 5 kilometers per second for that ablation to occur, and probably more like 5 to 7 kilometers a second. Obviously, the further out you go, the higher the velocity was during the initial stages of re-entry. So we got some here from South Australia. You can actually tell morphologically from South Australia and West Australia. There are subtle morphological differences in the amount of ablation. Here's a megalodon tooth. Big size. You wouldn't want to meet that, would you? Nothing to do with tektites, but they were found in the Ander area when I was collecting Ander tektites. Now, what else do we have to note here? This specimen here, this is from South Australia. It's the largest one from South Australia, third largest in Australia. You can see again, this has an equatorial rim, equatorial scars here, and a rim, not so well developed, it's been weathered a little bit, but you can still see the rim there. This is the size of some of the bread crust specimens actually, but you can see it's formed in a different way. Morphologically it's quite distinct. For me it's distinct anyway. I can see clear equatorial scars there. So very rare, unusually large Australite. Eventually I will send that back to Australia. I'm just enjoying it at the moment. So here we go. And so these Australian tektites, these are distal tektites. The thing that differentiates distal tektites is they were travelling sufficient velocity that they ablated. So the heat of re-entry caused the specimen to ablate and then spool as it was rapidly, once it lost its inherited velocity, it's actually rapidly cooled in the upper atmosphere and then spools. So this is what differentiates the distal tektites, the ablation. So here we have many examples smaller examples. If only I could zoom in, I could show you much better pictures. We got lots of australites here, cores, mostly cores, some flanged bodies. All the flanged ones are small. Oh dear, they're rolling off. More in here. Again, I've probably got too many, but I don't know if there is such a thing as too many tektites. My wife would say there was. When you've lost the flange, you get a kind of lens without the flange there, either a lens or a core. On the small bodies, you call it a lens. So, right, anyway, so just to recap quickly, we had the I'll do the recap in a second. Okay, so we've moved in terms of distance from close to the crater to the distal tektites that we find in Australia, which are in the order of up to about 6,000 kilometers from the impact site. Now let's put it in context. Let's go from time of formation. So the most distal tektites, the australites, were actually the first formed. So distal tektites, what are they characterized by? They were traveling at the highest velocities. So first formed tektites from the shallowest depths, traveling at the highest velocities. The most imparted energy from the impact went into these tektites. So they're defined really by the fact that as they were ejected, they were flattened just very slightly by atmospheric interaction as they exited the atmosphere. They then re-entered at velocities in excess of 5 kilometers a second, let's say 5 to 7 kilometers a second. They were ablated, the front melted and flowed backwards, creating a flange. They were then very rapidly cooled once the inherited velocity was lost, and then they spooled and they lost their front shell. Only a few of the classic specimens, like these buttons, retained their flange. So the distal tektites are really characterized by the ablation due to the high velocity. Then we move on to the medial tektites, typical Philippinites. Now these were ejected at lower velocities. Basically, in terms of plastic deformation as they were ejected, which is all to do with the atmospheric interaction, this varies from nothing effectively to a reasonable amount of plastic deformation, deforming a sphere into an ellipsoidal type shape. The key thing with this is when they re-entered, some of them were still molten. The largest ones, they were not molten on the surface, because clearly there wasn't any secondary plastic deformation, but they were clearly red hot or molten inside in the very largest specimens. The vast majority, which are on the smaller size in terms of a few centimeters across, these had solidified prior to re-entry. During re-entry they were heated, but not sufficiently to ablate the specimen. They were then spooled once the inherited velocity was lost. So the key thing with the medial tektites is the spallation. We get the same spallation in the distal ones, but these ones, because they haven't suffered any ablation, the spallation is different. So you get these kind of lenticular cores, whereas in the distal ones you get these distinct equatorial cores because they've had the preceding ablation phase. Next we move on to the proximal setting. Now here are the proximal tektites. Now these proximal tektites, they're typified by Indochinites. Now these were the last formed tektites, so they might have been deposited closest to the impact, but they were actually the last formed tektites. We know this because these have the lowest beryllium-10 content. So you would expect in a normal sequence of rock for the highest beryllium-10 content to be in the sediments closest to the surface, because they are the youngest sediments. Beryllium-10 is cosmogenic isotope. It then decays, has a half-life 1.39 million years. It decays over time, so the deeper sediments get lower and lower abundances of beryllium-10. So these Indochinites have a low abundance of this cosmogenic isotope. Therefore, they are effectively the deepest excavated rock, which has to be the last excavated rock, because you have to excavate the stuff above first. So these ones here, as you can see, you get a lot of discoidal shapes. These Indochinites, they're very much defined by their plastic deformation, their interaction with the atmosphere. In fact, many probably never truly left the atmosphere. Then I've lost my trail of thought there. Yeah, so they're very much defined by the plastic deformation. In terms of reheating, well, many were probably molten as they were climbing and as they were falling down. They were probably not significantly reheated, but clearly the exterior shell cooled whilst they were still in flight, and in some cases it appears to have been reheated on the anterior, so you get this minor, very minor spallation on the anterior margins of many of these tektites. So the main defining thing of the proximal tektites is the plastic deformation, which was very significant. Moving on, then the most proximal, the last form tektites are these layered forms, these Mung-Nong type layered tektites. Now these have an even lower beryllium-10 content, so it's very clear that these are the deepest excavated last form tektites, the lowest energy. The crater is opening up, the energy is more widely dispersed, so these were ejected with the lowest velocity. It's probably still went up to heights of 20 kilometers plus before falling down. They're all ballistically ejected. They didn't form in place, in situ. They are ballistic ejector as well, but they weren't heated to sufficient level to create droplets, and in fact you still find some detrital grains in these Mung-Nong type layered tektites. So they're the last form tektites. Distribution isn't even. They're going to be predominantly going along ejector rays. So distribution is never perfectly even in a strewn field.